Hello and welcome. I'm Quinn. I'm a coach at Major League Hacking. I'm really excited to have you all here for this stream. And this is a really special stream because actually I'm not running it. This is a stream introducing generative adversarial networks, and it's going to be run by Yash, who is an active hacker in the MLH community, and they're doing a guest stream for us, which is going to be super exciting. So without further ado, I'm going to welcome Yash up to the stage. Just before that, I want to highlight, please do check into this. We'd really love to see loads of people checking in. I sent the link out in the chat again, and I'll pop it up on the screen now. But with that, welcome Yash.
Hi. So, hello everyone. I'm Yash. I am a hacker from India, joining in from India. Let me know where you all are joining in from. I see a lot of highs in the chat. Okay. Um, and yeah, so I am Yash. I am a hacker joining in from India, and this is my very first stream. So I am very excited about that. Um, if you've joined in previous like GHWs and previous streams of the GHW, you might have seen me around in the chat. I go by the name of 44 Not Found. But for now, today, I'm going to be here first streaming for the very first time. I see a lot of hellos and a lot of familiar faces. I see Green Yoshi, Flying Girl, hello, hello, hello. I see Ashish, hello, again. Okay, awesome. So with that, um, okay, awesome. So I think I'm all caught up on chat. So with that, we're going to dive into today's stream, which is about GANs, which is about generative AI GANs and centered around pizza because obviously it's got to be around pizza. Okay, that was a lot of rambling. So let's talk about what today's stream is going to be about. So this stream is essentially broken into two parts. The first one is going to be having an intuitive understanding of how neural networks really work. How what exactly is a neural network? And if you've been to the previous streams by Bully, run by Bully, you would have seen a lot of material overlapping. They did an amazing stream on neural networks earlier this week, so I would highly recommend watching the recording of that stream as well. And then in the second part, we're going to be exploring how GANs work, and how we're going to be creating how they create images and data and stuff. I see a question here. How long is this workshop? So this workshop's going to be around an hour long. It might go a bit above that, but I'll try to keep it under an hour. So hopefully that answers your question. Awesome. So with that, that's the stream plan for today. And we're going to dive right in unless anyone has any questions. So if you have any questions at any point in the stream, feel free to put them in the chat. I'm always monitoring that, and Quinn's here to help me monitor the chat. So I'll answer that quickly. What models are we going to be using? We are actually not going to be coding anything at all. This is essentially a theoretical stream. I know that's probably a big bummer, but this is a theoretical stream that we use to try to get the intuitive ideas behind behind generative AI, get GANs and generative AI in general. What's my favorite pizza topping? Okay, so I sort of expected these questions, and we are going to talk about them towards the end. But because we have a lot of material to cover, I think we're going to dive into the stream from now. But I will come back to these questions in just a bit. Okay, awesome. So with that, let's talk a bit about neural networks. What are neural networks? And I would love to see y'all say what your understanding of a neural network is. What do you think is a neural network? I'll give just a few minutes for people to type in the chat what they think a neural network is. Gradient descent. Okay, that is indeed a correct answer. Human brain, but very, very small. That is also a very good answer. Mimics brain cells. That's a yes, absolutely. I love these answers. So essentially, neural networks are artificial neural networks, as we call them, mimic the way that your last three brain cells. Okay, I love that answer as well. So neural network, the way that it works is it essentially mimics the way our brain processes information. And it's essentially a really cool and elegant algorithm that manages to learn patterns from data. And you might have seen this image everywhere before. So this is a neural network. This is an image of a neural network. And in this, you'll see these tiny little circles, right? So these tiny little circles are something that we call nodes or neurons. And within these, there's an input layer of neurons inside of a neural network. And then there are hidden layers, and then there is an output layer. What are these? We will definitely go a bit deeper and look more into the neural network part after this. So for now, all that you need to know is a neural network is made up of nodes, neurons, and then it's arranged into layers. So there are hidden layers, which are layers that are not visible to the user, and then there's an input layer and an output layer. Okay, hopefully that makes sense. I see another very familiar face from Pharaoh, and which is talking about me loving pineapple. Um, Thank you for the best wishes. I do appreciate that, but I do very much love pineapples, just not on my pizza. Okay, again, we will take all of these questions towards the end of the stream. So let's try to build a neural network from scratch. Okay, let's try to build an idea of a neural network from scratch. Let's say we have a friend. Okay, her name's Alice. And Alice, what Alice wants to do is she wants to identify when she's going to order a pizza or not. Okay, and for that, we want to make a model that's able to sort of predict when Alice will order a pizza. Now, this is a simple mathematical model. There's nothing AI about it. There's no learning here. We just want to build a simple mathematical model on when Alice will or will not order a pizza. And we do that by the following method. So firstly, we go to Alice and we ask her, okay, can you tell me what are the input factors you consider before you order a pizza? And then Alice says, okay, I consider how much am I craving pizza. So how much do I want pizza at that very moment? And then Alice is also health cautious. So Alice says, if I've ordered a lot of junk food in the past few days, then maybe I wouldn't want to order pizza as much. And the third thing is her hunger. How hungry is she feeling? So she considers these three inputs when she's deciding whether or not she wants to order a pizza. Now, these inputs are again very subjective, and it won't help us make any sort of a classification or an indication of whether or not Alice is going to order pizza. So, what we do is we ask Alice to essentially put it on a scale of 0 to 10. How hungry you are between 0 and 10. How much do you want to eat? How much junk food you've eaten in this from 0 to 10. That sort of thing. So we ask her, okay, what is the input range? How much are you feeling that? Can you quantitatively tell us how much you're feeling that? And then for Alice, not each one of these input example is going to be of the same importance. So maybe Alice puts more importance on cravings than she does on junk food, or maybe she puts more importance on junk food than she does hunger. So with that, we're able to essentially introduce another metric, which is weight. And what weight is essentially a measure of the importance of each input. So weight isn't restricted from 0 to 10. It is supposed to be for between like anything. It can be negative, it can be positive. It is essentially telling us how important that particular input is in the consideration of the output, right? And so when we sort of put this together in a representation, it ends up looking something like this. So it ends up looking like we have our input nodes towards the left here, which have the input values, of course. And then we are connecting these together to the output. And the connections themselves are the weights. The weights, again, the weight is the quantity that tells you how important a particular input is in the consideration of the output. And with this, we are, able to sort of create a visualized model of whether or not Alice is going to order pizza. But okay, so we have these numbers here, and we want to figure out an output value. So how do you think can we do that? How do you think what sort of a some mathematical operations can we perform on these three six values that we have here, so that we get an output that will give us like an indication of things? What do you think about that? Oh, I see a lot of questions. Um, Okay, so Permatis is asking firstly about explaining weights, biases, and in input and output. So we are going to do that. Permatis is then asking, why do we get negative? So we get negative value because essentially the more junk food that Alice is eating, the less likely she is to order a pizza. So she's putting a negative importance on junk food instead of the other inputs. So that is why we are indeed doing this. We are adding a negative weight over junk food. Then Permatis's next question is, where do you get the weights for her pizza decision? That is a very good question. Where do we get this weight from? For now, you can think of weights as being gotten from her past. So we looked at her past pizza ordering habits, and from that we were able to determine, okay, uh, she puts this much importance on craving, she puts this much importance on junk food, so on and so forth. But we're going to look a bit more into how weights really work in the next few slides. Awesome. So I think I am mostly caught up on most questions. Awesome. So I want you to answer this. How do you think can we take these few numbers together and sort of perform some sort of a mathematical operation that gives us an output value, which isn't supposed to be like anything. It's just supposed to be a indication of whether or not you're going to order pizza or not. Does that sort of make sense? Tomato says this is multiple linear regression with one output. That is entirely right. Indeed, this is exactly a regression model. This is a linear model. There is nothing AI about this. We are trying to build up to a neural network, but for now, this is just a linear model. So what we do with this is essentially we take in the input and then scale it by the weight, because weight is again the importance that you're putting on that particular input value. So what we do is we take in the weights and then multiply them by the input value. So we are scaling the input with respect to the weights, and then we add them all together. So this is essentially taking a weighted sum of all of the inputs. We're taking a weighted sum of all of the inputs, and that gives us a really cool output value, which we can use for an indication of whether or not we want to order a pizza or not. So the indication, so like how do we know? Okay, we got a value of 12.55, but what does this really even means, right? So what we said in our original output function was that if the output value is greater than 0, then the node will be activated and it will be a yes, okay, we are going to definitely order a pizza. And over here, this value is definitely very much bigger than 0. So that definitely means we are going to order pizza. Alice is very likely to order pizza. Great, awesome. But then, so we have a sort of indication on whether or not Alice is going to order pizza. But then something actually goes wrong with this equation, and I think Permatis has a indication. So Permatis says, "Do you consider anything above 0 to be yes, even if it's very low?" And this is exactly the thing that goes wrong with this equation right here. So let's try to understand it with another example, right? Let's say we have another friend, Bob, right? And Bob doesn't really care about the amount of junk food he eats. What Bob care about is the discounts. He's very financially aware. So he cares about what discounts are available on pizza before he makes the decision of buying one. So you will see that all of the weights here are positive because we replace junk food with with discounts, which is, of course, if there's more discounts, then there's going to be more likely that Bob is going to order a pizza. So what we've done is all of the weights here are positive and all of the inputs. So we don't have any inputs right now, but we can get inputs and then we can plug it in our formula that we have, and we can get our value of, we can get our indication value essentially that says whether that determines whether or not we are going to order a pizza. So if we, visualize this, it would look very similar to what we saw originally in the Alice example, where there's craving, discounts hunger, they are fed into an output, and then the weights are the connections the weights are the connections which are essentially the importance that you're putting on that particular input, and then you get an output. So when we represent this in the form of like an X, Y, and Z, what happens is what Pomatus says. So when X, Y, and Z are really, really small, something goes wrong. So for example, if the value of X, Y, and Z is like 0.001, the value is above zero. Let's look above the mathematics and try to see what's really happening here. So Bob is like barely hungry. Bob is barely craving any pizza, and there's like no discounts at all. So what these values of 0.1, 0.01 actually entail is the fact that all of these inputs are at a very negligible amount. But because all of the weights are positive and all of these values are positive, they can only be between 0 and 10, right? So all of these values are positive. This value is always going to be positive. So our output is always going to be greater than 0. And because our metric is about the value being greater than 0, that means Bob is going to order pizza. Bob is more likely to order pizza. Our model can never get a negative value. That means our model will never predict that Bob is not going to order pizza. Our model is completely flawed because, again, it does not understand that there could be a time that Bob is not going to order a pizza. Okay, so why did this go wrong? What happened? Why did this go wrong? Are there any why do you think we made a weighted sum and then something went wrong here? What went wrong? Do you have any? I want to ask chat. Do you have any sort of idea as to what went wrong? I'll give a minute for people to type in. Um, okay. Um, Not enough training data. But we don't have any. So Permatis says that we don't have any enough training data, but we didn't even use the training data. Right? These weights, you can think of it as somehow getting the weights. Just we managed to guess the weights randomly, and these weights are right. So that's not really what went wrong here. We are not really using training data here. Emotions fluctuate. That is also a good answer. So what Permatis is saying that the value is between 0 and 10, and the numbers are always going to be different, right? But but so what Permatis is essentially saying is you can't map the qualitative feel of emotions quantitatively into a number. That can't really work. Yes. So it doesn't really work like that. But our model is even more flawed than that. Our model is so flawed, in fact, that no matter what, it is just not able to identify when Bob is not going to order a pizza. And that happens because of this value over here. We say that our output is going to be greater than 0. And that is the only time we are going to order a pizza. But where did this value come from, right? It's not necessarily going to be 0. It could be something else. This value is not essentially the most optimal value for every single use case. That's just not possible. It would be variable. So what we do is we introduce a new sort of value, and we call that value a bias. So instead of our node activating for a weighted sum is greater than zero, we only activate our node for our weighted sum is greater than the bias value, whatever that bias value may be. And the bias value, you can think of it similar to be to the weights. So essentially, it is a value that we will understand, we'll find out from looking at the past history of ordering pizza by Bob. So we use that as a guide to figure out what the bias is. And then all we do here, because this equation isn't all that good, the bias would be different for every single node, right? It would be different for every single model. What we do is we sort of generalize it. We subtract bias from both sides of the equation, and then we get a weighted sum minus bias is greater than zero. So we are back to this zero equation here, but these two equations are not the same. This equation has an added bias because the zero originally was an arbitrary value. And what we did here was we added this bias so that it could in case like there are only positive weights, or if values are really small, or there are only negative weights, so something goes wrong like that, we have that bias to be able to sort of course correct our model. It's sort of a threshold value about which we say, oh, yes, it's going to be a yes, or it's going to be a no. Bias is in which range of numbers? Okay, so I am I'll admit I'm not entirely sure, but I don't think there's entirely a range of for bias. It could be any value as long as it's just like weights. So it's helping our model become more correct over time. And we'll take a look at how weights and biases are trained. So how weights and biases come to be, how it's not really, we don't really go ahead and ask our user, right? How do we do this? Like what importance do you put, or what bias it is? So we use AI training, and we're going to take a look at that. But for now, what we do is we take a weighted sum and subtract bias from that to get an output value that we can then use to indicate whether or not Bob is going to order a pizza. So with that, we can then redefine our output function, final output function, to be something like weights multiplied by the inputs minus the bias value. And if we even concise it a bit more, it looks something like weights multiplied by input minus bias. Now, this is very very fun thing. Does this remind you of anything? Does this equation remind you of a very very popular equation? So Permatus has another question. Do we use any kind of p-value for this model, such as p is less than 0.05 equals to significant one? I am not entirely sure, Permatus. Could you explain it a bit more? I'm not entirely sure what you're talking about. CGPA calculation. Yes, yes. So Ashish says this is a CGPA calculation. So in other words, what this is an equation of a line, a singular linear line. If you might have recognized it better in this format, where y is equal to mx minus c. Dave says this is a slope intercept equation. Yes, you're absolutely right, Dave. This is indeed a linear line, and that is why this model is called a linear model, because at the end of the day, it is just a line. It is a line drawn on a graph to best approximate the data point. So it wants to reduce the most number of errors, but at the end of the day, it's just a singular line that is able to model the data. So a singular node, you can think of that as a linear model in and of itself. So hopefully that makes sense. Any questions? I'm open to take them now. What happens if model is equal to zero? Then we don't get a yes or a no. That is very hard that the value is exactly zero. But what happens there? I think it will make more sense. But what happens is the model thinks it is equally likely to get a yes as much as a no. But I don't think in practice it's ever essentially possible to get a value of zero. because of the weights and bias, at least one of them would be a non-zero value. So at least if bias is non-zero or the weights would be non-zero. So I think, and correct me if I'm wrong here, I might be wrong here, but I think in practice we don't really get a value of zero for our output. Okay, awesome. So I am taking this time for questions. Are there any questions that I can? Does everything track till here? If there are no questions, send an. I'm going to steal what Quinn did. Send an emoji in the chat. And I'll know that you understood something. You can make the bias half of your output range to make it a switch. True. Yes, indeed. Um, we are going to be looking like at something like that towards the next part of the stream. But yes, you could do something like that. Emojis. I see Way in the chat. Is it replying with the pineapple on pizza emoji? Which I don't know how offended I am supposed to be by that. But okay, awesome. So I see no more questions. So I'll continue for now. Okay. So how do nodes work together, like in a network, right? So, okay, we understood how nodes work at once. So a one node is a linear model that takes an input and gives out like an output. It takes in a bunch of input and gives out an output. But how do nodes work together in this network, right? So say, for example, you're making a neural network that like classifies between cats and dogs. So in this case, what each node essentially does is division of labor, right? So what it does is it takes a smaller chunk of the problem instead of each node trying to identify if it's a cat or a dog in and of itself. It essentially divides the labor into smaller parts and tries to do that in itself, tries to do that small part and process that data and pass that data on to the next. So to understand that, let's take this example of a network that classifies between cats and dogs, right? So there are different layers, right? So say, for example, the first layer only detects edges. Now, I'm not saying that's how neural networks work. um, it's not sure, like you don't know if it's definitely going detecting edges, but for the sake of arguments, for the sake of understanding, let's say that's how neural networks work, right? So the first little node over here, let's say what it does is all it does is it tries to detect this tiny edge over here on top of the dog's ear. And the second node, let's say what it does is it tries to detect this tiny edge over here. So what these two nodes together are doing is one is trying to detect this edge um, of my cursor, if you can see my cursor, and the other is trying to detect this second edge. All it's trying to do is trying to detect these two edges, right? But what happens when you have these two edges is once you've like detected those, you can sort of take the output of that. So the first oops, I misclicked, but okay. So the first node essentially says, okay, I am sure that this edge of the dog was present. And the second node says, okay, I am sure that this other edge of the dog's ear was present. And then they can take those outputs of that sub part of the problem, and then they input it as they take the output and input it into the next layer, which could do something like detecting shapes. So it would take these two inputs of the nodes. So like the um, the ear, first ear, the first edge, and the second edge, and it can look that both of these edges are present. And then this node can say, okay, I'm pretty sure that the dog's ear as a whole, as a shape as a whole, exists in this image. So I'm pretty sure that the dog's ear exists. So you can think of layers as doing part of the work and then passing off, passing on that other part, next part to the other layer, which does the next part of work and then passes off as an input. Hopefully that makes sense. Okay, I see more questions by Mattis. Um, I don't get this chart. Isn't it the same with one response slash output value? Like yes, no, dog, cat. I am so sorry, but I don't entirely understand your question. Are you referring to this chart right here? Please explain what happens if we add complexity like cat, dog, turtle, car. Okay, so what happens when you add more labels, like more categories for the model to classify between? Are you asking about that? If we do add like more categories, what essentially would happen in that sort of case is like what the hidden layers are doing are they are extracting features. So maybe some part in this network would become really good at extracting the feature that of a cat's whiskers and nose. And maybe some part in these in these nodes would become very good at extracting like a car's shape, the wheels and the headlights, that sort of thing. And so overall, it would then at the output layer, these neural networks, like the neurons, would work together to sort of be able to add between different to classify between different categories. But would hidden layers become bigger by adding more categories? So generally, I'd say it is dependent a bit on what is sort that you're trying to do. The hidden layers architecture, so there's like I'm sorry, I'm blanking out a bit, but I would say that the hidden layers have a sort of architecture. So, for example, there's CNNs and stuff that helps you. Okay, let me take a pause here. I will definitely get back to you on this. I'm not able to verbalize it properly, but I will definitely get back to you on this question. So thanks for asking this question. I do really like that. What happens, but I will get back to you on this. So I am sorry for cutting off your questions, but we do have a lot of material to cover. I would like to just increase the speed of it a bit. But if we have time at the end, I will be very glad to take all of your questions. Okay, hopefully that makes sense. Okay, awesome. If I see no more other questions, so for now, I'm going to continue on with the slides here. So okay, what I talked about right now was having a bunch of linear models, which all work together, and sort of work together to, at the end, be able to classify between cats and dogs and all that sort of thing. But something goes wrong between this. So if you have like a first layer of neural network, right? Well, we saw what the equation looks like. So it has weights and inputs, and then we subtract the bias out of that. And then if we looked at the second neural layer of neurons, what it has is second set of weights multiplied by the second set of inputs minus the second bias. But what happens is the set of inputs. What this really is essentially the output of the first layer. Right? You're taking the output of the first layer and you're inputting it into the second layer. So then this second layer of a neural network essentially becomes expands out to be this, which is the weight multiplied by the output of the first layer. This is just the output of the first layer minus the second bias of the second layer. Okay. Yes, very much. It is sort of recursive function. Not entirely because the function isn't same. The set of weights and set of biases are different each time, but you can think of it as recursion. And then the second set of neurons are fed into the third layer, so on and so forth. So at the end of all, what a neural network really becomes is this big mess of equations, which is all the weights multiplied by the input. The input is just the pixels, the input pixels, right? Minus the bias. Okay. So when you sort of look at this equation, right, it looks so big and threatening. But if you think about it, what's really happening? Well, all of the weights are constants, and all of the lost connection. Can someone let me know if my connection is might seem to be
I
worrying me?
think you're buffering a bit, and I can't quite tell if it's. I think you're back now. I think we're looking okay.
Awesome.
We're back. Okay, right. I'll leave you to it.
Awesome. So I am sorry for that internet problems, but as they said, I am back. Yes, I am indeed back. Um, awesome. Thank you all for letting me know. So what we were talking about is that all of these weights are essentially constants, and all of these bias values are also constants. So if you multiply constants together, you will at the end of the whole thing, you'll get a big constant value. And if you multiply and subtract all the constants together, you will also get a big constant value. So if you collapse all this equation into one tiny thing, you get something like this, which is the final network is some weight value multiplied by our original input minus the final bias value, which is both of these are constants, right? And if you can remember what this equation reminds you of, this equation is again an equation of a line. It is a linear equation. It's just one line. So what's happening is we did all this. So we made this big neural network with all these linear models, and then we sort of, when we calculate what happens, it just ends up becoming a big linear equation. So all this is doing is, again, it can only model a singular line. It can't learn non-linear equations, can't learn non-linear data patterns, and that's not ideal, right? So what we do is we start to input in a activation function. And what a job of an activation function is essentially to introduce non-linearity in our models so that it can model more complex patterns inside of our neural network. So our neural network is to stop our neural network from being this big linear equation. It's just a line at the end of the day. What we do is we introduce non-linearity by the methods of something called an activation function. So there are essentially another there's essentially two types of activation function. The first is what you apply in the hidden layers, which does what we talked about, which introduces non-linearity. And then there's another type of activation function, which we'll talk about in a bit. But you apply that towards the output of our entire network, so that you get a better number instead of just a output value. You get a number that you can actually understand and use. So the examples of both of them are here. So firstly, we have ReLU, which is a piecewise linear function. So it's linear from 0 up to infinity, and it's linear from minus infinity up to 0, but it's non-linear on its global scale. So on its global domain. So essentially, when we apply ReLU at our nodes, at the output of our nodes, before feeding it to the next layer inside of our hidden layers, right? That manages to inject just enough non-linearity required for our model to be able to learn more complex patterns. Does that make sense? So if you look at ReLU, right, all it's really doing is it's saying, okay, if the output value of a node is greater than 0, then just pass on the same value on to the next node. And if the output value is less than 0, right, then just pass on 0. Don't pass on the negative value. Just pass on the value of 0. And that sort of ensures that some of the nodes are activated. That's why it's called an activation function. Some of the nodes that are positive, right? They are activated and they are passed on. And the nodes that are negative, well, they are not activated, and the input of that is not passed on. It's just 0. And what sigmoid, this other type of neural network, does is that what sigmoid is, and it is used in the output layers. So what it does is essentially you have an output of greater than 0 and less than 0, right? So you know that if it's greater than 0, then your model thinks, yes, the classification is going to be a yes. It is confident in its classification. But if you get a value of 2 versus a value of 6, right? You don't really intuitively get what does that really mean? How confident is your model? So what sigmoid does is essentially it takes that output and it maps it between a value of 0 and 1. So it essentially gives a value. If nothing makes sense, think of it this way. What sigmoid does is it takes the output value of the entire big calculation that we just did, and it outputs out a value of probability of how probable does the model think this particular event is going to happen. And it's going to output that value out in, and because it's probability, we are easily able to understand what's being talked about. So if there's a probability of a rain, it's greater than 0.5, we can say, okay, now we know that it's probably going to rain. If it's like a value of 0.9, we know, okay, now it's definitely going to rain. And if it's a low value, it's like probability of 0.1, then we can be sure, okay, it's not going to rain. Hopefully that makes a bit of sense. So to quick recap, ReLU is used for introducing nonlinearity in hidden functions, and sigmoid is used to introduce to sort of give an output as a probability in classification, binary classification problems. Okay, awesome. So if in our cat and dog example right here, we would apply ReLU in the hidden functions over here, in the hidden layers over here, and then some of the nodes would be activated, some of them would not be activated, and we can take all of that input, pass it on to the final output layer where we apply softmax. So softmax is a bit different than sigmoid. For now, we can ignore it. Just think that it's giving us probability. So what sigmoid does is it gives us probability in binary classification problem. Softmax gives us probability in multi-label classification problems. If there's more than two categories, it's able to give probabilities for that sort of a function as well. So then we are able to get the probability of how likely does the model think it's a cat versus how likely a model thinks it's a dog. With that, we have a basic understanding of how a neural network really functions. Okay, are there any questions still here? I see a bit of questions. So sigmoid, Permatus asks again, sigmoid is how confident from 0 to 1 it is on the output, 1 is equal to 100%. Yes, that is probably a good way of thinking about it. 1 means 100, model is 100% confident. That's going to be the classification. And 0 means it's really not 0% confident. You can think of it that way. Formatus again asks, so if one node is not activated or it's alone and not connected to both the input and output, this path is blocked / not used. Yes, you can sort of think of it this way. So if we go back in our previous example, right, think of it that this particular node, what it did was it detected the edges on a cat's whiskers, right? All it did was detect whether or not those whiskers were present or not. And you see in this image that we are inputting it finds no whiskers, right? There are no whiskers. So it doesn't make sense to pass on the input of this out onto the next layer of our neural network. So we just deactivate that output and don't pass it on. Okay. Quaker says, yes, totally makes sense as probabilities. Awesome. Glad that it makes sense. Okay, so now we come on to the next question, which is of what weights do we choose when we're making a neural network? And this is where the AI part of all of it comes together. This is where the learning happens. So essentially, let's think about it this way. What we did in our Alice and Bob scenario was we maybe went and asked Alice, how much do you think how much sort of importance do you put on this particular input. But if we were, say, making a neural network that was predicting whether or not it's going to rain today, well, oops, my bad. Well, in that case, we wouldn't be able to sort of ask the rain how much importance do you put on this particular input before you start, before you like get out an output, right? You can't use that to make a classification. So instead, we want a sort of method that we can use for our AI to automatically learn how exactly a particular classification works. So we want it to be able to update its weights and biases on its own. For that, we're going to take this example of a neural network that predicts whether or not it's going to rain with taking in three inputs. The first is the value of pressure. What's the pressure, air pressure? The second is the humidity value currently. And third is the temperature right now. And when we take all of these values, right, and we put it in this neural network. So you can think of this big blob as a neural network. What we are essentially doing is, say for example, let's see what happens when we put these values. So we have on the left here, we have a sort of vector, which has the pressure values on the left here, the humidity percentage in the middle, and the temperature on the right. And we are feeding it into our AI model, and we are getting predictions in the probability, right? We use sigmoid to get probability. But these predictions are like completely random because the AI model starts with completely random weights and biases. It doesn't know what it's doing. So we need to somehow train it so that it gets better at stuff. And so we introduce something called a loss function. Loss function, you can think of loss function as essentially a way to model error. How bad is your AI model at performing, or how good is it at performing? And if you take a test, right? If you take a test, a true or false quiz of like 100 questions, right? And you do that, you give it to your teacher, and the teacher scores it and tells you, okay, you got 85 of the questions right and 15 of them wrong. So what you would want to do is you would want to optimize for that 15 wrong questions, right? You would want to reduce that value. So what you're essentially doing is you're using accuracy as a loss function to optimize for your own learning, for the test, right? And we could use accuracy over here, but it just wouldn't work that well. And why would it not work that well? Is the most feedback that our AI model can get is that it was right or it was wrong. There's no sort of a granular method for our AI model to be able to learn from that metric of being true or false. And so because of that, what we do is we employ a different sort of function, which is called the cross entropy loss function. And this might look like it has this formula and it might look very intimidating. But for now, all I want you to think about is this one key idea of a loss function. And this is going to be really important because we're going to come back to this. And that key idea is that we want to punish our model for being overconfidently wrong. So, for example, what really happens is if our model predicts like there's a 92% chance or a 0.92 probability that it's going to rain, and it doesn't rain that day, well, we want our loss value, our error value to be as high as possible. If we are uncertain and if our model is uncertain but correct, we still want to punish it somewhat, but not a lot. We still want to punish it a bit. And if our model is confident and it's correct, then we don't really want to punish. Our error rate is going to be really low. So these are the values that we want to optimize for. And if you look at the graph here, right, think of it this way. As we get closer and closer to zero, what is really happening is our model is essentially making more and more mistakes. So it's more and more confident in being wrong. And so the error rate is increasing exponentially as we move towards the left. And as we move towards the right, our model is getting more and more confident and being right, right? So in that case, the error rate slowly trickles down onto zero. The what log right here does is it allows us to do this. Gives us a really cool graph that allows us to sort of punish our model more for being overconfidently wrong. That's what loss functions does. Loss function is nothing but a metric to allow us to model our errors. So moving on. Okay, so now that we have a loss function, right? How exactly do weights work? How exactly do we sort of optimize our weights? Okay, so essentially we know that we're doing something wrong. We know how much wrong we're doing it. All that's left is to change our internal structure, internal inputs, so that we can get more closer to the actual correct output that we want to, right? Um, and to do that, what we need is we need some way of knowing how much did every single weight in every single node contribute to the loss function. So that might be a bit of a hard idea to think of. Um, and what we are essentially doing is we have everything. All of this is essentially one big equation, right? All these inputs are being fed into. All these outputs are being fed as inputs in the second layer, and the outputs of that are being fed into the output layer, and so on and so forth, right? And all of that was that one big weight equations of weights and biases. And the only real input is these factors that we're taking in at the start, right? So what we do is essentially we have all this input, and we then try to calculate how much did every single weight contribute into that loss function, to that error rate that we call, and we call that calculation a gradient. So Quakers asks, so the confidence level is the feedback since digital 0 and 1 doesn't average correctly. Sort of. Could you, a clarifying question, could you explain a bit more about what you mean that the 0 and 1 doesn't average correctly? And then Quaker says, woohoo, partial differential equations. I completely agree with this statement. I love partial differential equations. So what gradient is essentially is doing here is it's partially differentiating the loss function by the weights. Now you don't need to know anything about the partial differentiation, what a partial differentiation is. Think about it this way. Um, if you have like a velocity, right? Velocity graph, and you take a slope on that, you get an acceleration, right? You get the value of an acceleration. And so what really happens is, okay, I'll quickly address this message. You said that it was difficult to determine a good training number. 0 and 1 was limiting. Oh, I still don't quite understand what you mean. Do you mean training number as in the bias that we are trying to train? So you go to this to give probabilities as a gradient, then use that as feedback. Yes, absolutely. You use probabilities as a gradient. You use the loss function. So you're essentially using this function right here, and then calculating the gradient. So the probability that you're feeding into this loss function, well, that probability is just the weighted sum minus the bias and then applied with the activation function, right? So that's what the probability is. The probability is in itself a function, right? And so you're taking all of this big loss function and then you're partially differentiating it with each weight. And for now, just think of partial differentiation as something that allows us to know how much this particular variable result like contribute towards. So if I have a big function, right, of f y, like f of x, y, and z, and I got a value, then I can partially differentiate it with respect to x to get a value that would tell me how much did x contribute to this final value of f of x. of functions. So that's essentially what partial differentiation is doing. It's telling you, okay, this particular weight contributed this much to loss. So this particular weight resulted in a very positive loss value. This particular weight resulted in a zero loss value. So it didn't really result in much. And this particular weight resulted in a negative loss value. So that's good. If it's resulting in a negative loss value, that means it's reducing our error. And so we can increase that weight, and we can decrease the weight that's resulting in a positive loss value, like it's increasing the loss. And so that's sort of an optimization function of bringing the weights up and down and the biases up and down. And that sort of an optimization function happens by the process of something called gradient descent. And we use that to sort of optimize weights one by one together to essentially slowly, iteratively get a model that is closer and closer to the actual weights of our that we want it to be, that so that it gives more correct answers, more correct predictions. Awesome. So with that, let's recap quickly how we created a neural network. And we are already an hour in, and we haven't even started talking about GANs, so I apologize for that. But we have inputs. Each node has an input which has different importance called weight and a bias. Then the each neuron output passes through an activation function, which helps us bring nonlinearity. Then the error of this model is calculated by a loss function, which is basically the error rate, calculating the error rate. And finally, we then adjust the weights and biases by calculating their gradients. I see Finn saying, hey there, I joined pretty much 10 minutes ago. I understood what you explained previously, but couldn't understand the equations as I'm in high school. Finn, I think you really don't need to. So are you talking about this partial differential equations right here? So you really don't need to understand the maths of it. All you need to know is partial differentiation. Think of it as a black box for now. Okay. What the partial differentiation is essentially doing is it's essentially a mathematical operation you can perform on a function that tells us how much did each individual value contribute to the final value that we got. Like how much did each individual how much did each individual weight contribute in the final loss value, final error rate that we got? Does that make sense? I do apologize if I am missing a few questions because I am a bit. It is a bit stretched for time, so I will try to move on. But if we have time at the end, I will definitely take all of these at the end. Finn says, "Oh yeah, it does. Thanks. Awesome. Great. Glad it makes sense." Okay. So if there are no more questions, we'll quickly move on to the next part. So 1 hour in, and we finally talk about GANs. So let's talk about GANs. Ooh, okay. I'm sorry, I got distracted for a bit because I was talking about predicting about rain, and it started to rain over here very loudly. So if you hear any noise from that, that's just raining. So I apologize for that. Okay, so now the title of this whole thing: what are GANs and how do they really work? So, what our objective in generative AI is, of course, to generate new data samples, to make an AI model that can generate new data samples from a distribution. And then the AI would be able to sort of match that data distribution, right? So essentially, what we want the AI to be able to do is understand. Okay, so let's say we are asking the AI to generate cat pictures, right? So it must firstly understand what is a cat picture, and then it should be able to generate fake samples from the same distribution. So it should be able to generate fake samples of cat images. That's like our whole generative AI, like our whole objective with generative AI, right? That's what we want to do. But there are a few challenges in our current understanding of neural networks. Um, the first is we saw that our previous network was really good at modeling and classifying these sort of data, but it wasn't all too good at generating that data. And even if it was like able to generate the data, another big problem that occurs is that computers really love precision, right? So if you look at previous examples, there was either a correct or a wrong answer. Either the model predicted it correctly that it was indeed a cat, or it predicted wrongly that it was a dog when it was in fact a cat. Right. So that was something that we could easily train on. But the issue here is that there are an infinite. If you went to generate cat images, right, there are an infinite number of cat images that could possibly be generated. Right. So there's no one correct answer. So how do you calculate the error rate in something like that, wherein you don't know which image is correct and which image is false? So how do you exactly model loss or model the error rate in that? That's sort of another of a challenge. So what someone thought, what Ian Goodfellow thought in a 2014 paper was, let's sort of merge both of these problems together. So what we think is that what these two problems is that, one, our AI is really good at identifying whether or not a a image or a data or a classification is correct, like it matches the distribution or not. But when we go to generate it, our model sucks. It needs some sort of a hand holding, some sort of a feedback system that can tell it whether or not what image that it just generated was correct, whether or not that generated image matched the data distribution or not. So what Ian Goodfellow thought was creating GANs, which are generative adversarial networks. And what GANs are essentially is, it's not one model. It's two different neural networks, generally neural networks, called a generator and a discriminator. And what GANs do is essentially they pit them against each other. So the generator fights against the discriminator. So what the generator tries to do is it tries to create fake data samples from the distribution. It tries to create fake images, fake data samples that could pass off as the real thing, right? And then the discriminator tries to distinguish between a fake sample and the real sample. So with that, both of the models slowly improve by competing with each other. So if you've like trained an AI for a game before, say for example a Pong game, if you've done that sort of thing, you'll see that you let the AI fight itself for a bit of time, right? You let it play against itself, and then it learns its own exploits. And because it learns its own exploit, it needs to then improve that, because then its opponent will start to exploit those weaknesses, right? So it starts to learn. Starts to improve by competing with itself, and that was sort of a big insight that went into GANs. Let's try to understand this better with an example, right? Let's say we have two AI submodels. We have our discriminator and our generator, which are these tiny, cute little images that I generated. I generated both of these images for this stream. And these two AI friends, they want to make a pizza restaurant. They want to get started with a pizza chain. That's so tasty, right? But there's a problem with this. The problem is neither of them have either seen, tasted, or even like heard of a pizza in their life. They have no concept of what a pizza really is. So what we want to do is we want to somehow set them up in some way that they can work together to figure out what a pizza is and also make a good pizza. To do that, what we do is we pit them against each other. We divide the work. So the discriminator becomes the critic. It becomes very good at figuring out what is pizza versus what isn't pizza. And it's able to tell what is good pizza from bad pizza. Versus the cook. So the cook is our generator, which will fiddle around at random, it will bang pots and pans and it will burn up the oven and all that thing. And then it will like come up with a plate of something, just random goop, and it will show that to the discriminator and ask it, okay, do you think this is a pizza? And the generator will either go yes, that is, or no, that isn't. And if it goes no, then the discriminator would either go yes, that is a pizza, or no, that isn't a pizza. And from that, the generator can take feedback and improve over and so that's something happening. So essentially, the discriminator is against the generator. So these two are adversely, these two are enemies. And that is where the whole generative adversarial network comes from, because we are pitting two neural networks against each other. So let's see how the training process takes place. I see no questions. No questions related to the particular slides. So I'm going to continue for now because we are a bit pressed for time. But I will address a few of these messages towards the end. So let's look at the training part. Training part is about our discriminator, right? So what we do firstly is we take our pizza samples over here, which are from the actual distribution of actual pizzas, right? And we feed them to the discriminator, and with the label, right? So we tell the discriminator, okay, this is what a pizza is. So look at these few samples. We're not giving it a lot of samples. We're not training it for a long period of time. Just a tiny idea of what actually is a pizza, right? And we're giving those to the discriminator. And it eats that and understands, okay, I think I sort of understand what a pizza is. Now, a quick overview. The discriminator is just a classification model, a binary classification model. We just saw that in our first hour of stream. We just saw what a discriminator did. Discriminator is a classification model. It's exactly the same sort of architecture that works with with our model that predicted whether or not it's going to rain. So it's just the same sort of architecture that we are using over here. And with that, what we do after this, once we've showed it a bunch of pizza slices, what we do is we then go to the generator. And the generator again has random weights. It doesn't know what a pizza is supposed to look like. And so we input in random noises and we feed that to the generator. And then it gives that back as an output. The generator gives back a random output as an attempt at pizza. Okay. And I don't know about you, but if someone showed me this thing and told me it was a pizza and like said, okay, this is very delicious pizza, eat it, I would probably run away, right? I would not trust that dude ever in my life. So it starts off with very random models, with very random samples. So the discriminator itself, it isn't really sure if that's a pizza or not. It thinks it's not a pizza, but we only showed it a few images and a few slices of pizza. So it doesn't really know what is a pizza or not. It thinks it is uncertain, but it thinks this is not a pizza. And the core process, so what this whole process turned out into is something like this. So we have our generator, which is generating a fake sample, feeding that into the discriminator. And we have our set of real images. We're taking a sample from that and feeding that into the discriminator. And the discriminator's job is to identify whether the sample was fake or whether the sample was real. And based on that, once the discriminator makes the choice, makes the classification, we then reveal the answer of the generator and the real. We then reveal the answer to both the generator and the discriminator. And then we see if the generator managed to fool the discriminator, then the generator's loss goes down. And if the generator didn't manage to fool the discriminator, then the discriminator's loss goes down. So that's what happens. So essentially they both are fighting over the same loss over here, the same error rate over here. Does that make sense? I'll quickly pause for some questions because I realized that was a lot of information. So if there are any GAN related questions, I'll take them right now. Permatus asks another question. Question for the slide discriminator, are different models or same model fine-tuned in two ways? So Permatus, Indeed, the discriminator are two different models. So one of them is a generating data, right? It's sort of a regression model, and the other one is classifying data. So these two are sort of inverse of each other. So the architecture is, well, I wouldn't say completely different. They both are neural networks, and quite often both are convolutional neural networks. But yeah, they both are different models. Motion asks, how does the discriminator communicate with the generator? Does it directly adjust the weight? That is a brilliant question. I love that question. So yes, not exactly. So I think we will cover this part. So again in the future, like in the next part of the stream. So I do love that question a lot. That's a brilliant question. That's definitely the sort of question you should be asking. Okay, awesome. So I see no more questions. Awesome. So for now, let's quickly continue on to the next part, which is the training and adjusting process. So what happens is, we have a generator and it's iterating over and over, and it generates into the next pizza, and then it generates into the other pizza as well, so on and so forth. So over the course, over a period of time, the generator is able to slowly and slowly get better and better at generating pizza images. So it's at the end of the day, it's able to generate a very realistic looking pizza, and that's how it goes. But let's take a look at how exactly do they manage to adjust the weights. So I talked about they both work together to adjust their weights and then somehow be able to improve. But how exactly does that go? How exactly do they manage to adjust weights? So if we look at that, we get this big loss function, right? And at first glance, like this looks like a big sort of essentially a magical spell, right? But it is very similar to our original logics. It is essentially the same thing. And you can think of it as this way, right? All I'm going to do is I'm going to explain the terms here. What this is doing is this is taking the error rate of the discriminator and asking, okay, on average, how good was the discriminator at identifying real data when the images were actually real? And then what this term is how good was the discriminator at identifying fake images, at identifying generated data to be fake. That is all that we are doing. So what we're trying to do is the error rate here is the discriminator is firstly trying to maximize identifying good it's trying to maximize identifying real data as real and maximize identifying generated data as generated. Or it wants to essentially maximize those two values, right? And the generator essentially wants to do the other thing, right? So the generator wants to minimize this function. So what the generator wants to do is it wants to fool the discriminator. It wants to it wants the discriminator to say, okay, this data was generated. This data didn't really sorry, let me rephrase that. What the generator wants to do is it wants the discriminator to think all the generated data was real. So it wants to essentially minimize this entire equation that we have here. So both of these, if we look at like two key ideas for this, the key idea is that firstly, both of these models are fighting over the same value in a min-max game. One is trying to minimize it, the other is trying to maximize it. So only one of them is going to win. Okay. And the second very, very cool thing is because if and this comes back to what Musheng Moses asked, is when we model the generator's loss, we model it as this equation right here, which is that it's essentially trying to reduce the probability that discriminator thinks it's the thing it generated was fake. Okay, so it's trying to do that. So in its loss function, what you're doing is you're essentially taking in the discriminator as a as a parameter, right? In that. So essentially you've set GAN in such a way, the GAN in such a way that the generator can use the discriminator's gradients in its own learning process. So when you do the whole gradient descent process, right, and you try to calculate the gradients and then you try to figure out how to adjust the weights properly, you can sort of think of it as this way. It's not exactly the same, but you can think of it as this way. Say, for example, instead of the discriminator saying, I think your sample that you generated was I'm 70% sure that the sample you generated was fake. Instead of saying just that, it says, I'm 70% sure that the sample you generated was fake. And this is the reason. So I think the pepperoni's color was, blue, or the pizza was square in shape or something like that. So that's not exactly how it goes. I'm oversimplifying a lot over here, but you can sort of think of it as that way. That the whole part results in a more optimal training. Essentially, the generator gets like a cheat sheet of the judges' scoring criteria before it makes its decisions. So it's able to update itself a bit better. Quaker says it looks like exponential change discharge turn off, on and off, and through a continuous range of values. Yes, that is absolutely right. You're absolutely right there, Quakers. There's indeed that. I would have loved to go more into this if there's time, which I don't think there is. But if there is time and we want to talk about this at the end, we could probably do that. So once you've like had this loss function, right, with the generator and the discriminator. Oops, I think I lost connection there for a bit. Hopefully I'm back. Can someone let me know in the chat if I'm back?
Yep, you're all back. You're fine. Don't you worry. You're good.
Awesome. Thank you so much, Gwen. Awesome. So with this, once we've like have the log model, a loss model, right, we can continue with our gradient descent process. And slowly, our generator becomes better and better, and so does our discriminator. So both of them are trained at the same time, but slowly, our generator becomes so good, in fact, that it's able to sort of generate such good data samples, fake data samples, that the discriminator can no longer detect if that's a real or a fake sample. So that's at that point, we can do away with the discriminator. We've got a fully trained generator, and we can completely use that to generate new images. We have a trained model. That's it. Woohoo! We are done. Okay. So not quite. So before we, go on to the other part, this is really cool. I want to ask if there are any questions regarding regarding the loss values of our generator here. Are there any? If there are no questions, feel free to put an emoji. Okay, I do see your questions, Permatis. I completely understand that. For now, however, I'm not covering fine tuning. So maybe I think there was a really good session about with that I think Bully took about fine tuning. So you could probably watch that recording. So, but for now in GAN, I'm not going to cover that for now. So hopefully that makes sense. Do we always want the generator to win? Yes, we do. Okay, that's sort of a good question, because sometimes what happens is the discriminator is really bad at understanding what a pizza is. So think of your classification model being really bad. And in that case, right, then no matter what the generator does, right, the discriminator would say, no, that doesn't work. That's not good. We don't like that. Or the discriminator could say, yes, that's perfect. Even if it's really bad, the discriminator could say, yes, that's perfect. And in that case, right, we don't want the generator to win. We want the discriminator to become a bit better. But generally, yes, the end result is that the discriminator would become really good and the generator would become even better. That's our sort of end result. Does that does that make sense? Awesome. Okay. So let's talk about random noise for a bit. The random noise is what we sort of input in our model, our generator. So if you look at over here, if I go back a bunch of steps, you'll see in our generator, right, we are inputting in random noise. And we do that for a bunch of reasons, but the starting major reason of which is essentially um, our model is AI is again computers love precision, right? If our model manages to find like one data sample, one singular image, one singular pizza that is able to fool the discriminator over and over again and again, it's like the optimal pizza, right? Then the discriminator doesn't want to make like another pizza. Why would it want to do that? It can just repeat that same image or same data point over and over and feed and fool the discriminator. So instead, what we do is we input in a vector, a big vector value. It's a huge vector value as a random. So random input. So this is completely random values that you pick a random vector and you input it inside of your GAN, inside of your generator. And using that as an input, our generator generates different values, different images every single time. The cool thing about this vector is that if you have like a single z vector, so this is denoted by z. It's also called the latent vector. So if you hear me saying z or latent vector, I am just referring to the random noise over here. So if, say, for example, the generator took a random z value, a random latent vector, and then drew like generated an image, right? And I looked at that z value. I looked at that latent vector. So I stored that, and I gave that back to the generator. So I gave the same value of z again to the generator instead of a random value. In that case, the generator would make the exact same image that it did before. So if you've played Minecraft, that's the closest analogy I can think of it. You'll know that you can input in seed as well, right? Or like if you've played around with Perl and noise, you can input in seed and it uses that seed to generate a word, right? Or to generate noise. So this is exactly like a seed. And it's going to be a different seed every single time, but you can use same seed to generate the same image every single time or same data point every single time. And there are an infinitely different number of possible values of z. So we can create infinitely many distinct outputs again and again by using this latent vector, by inputting in latent noise. So we don't really have to worry about us running out of vectors and only being able to generate a specific number of images. And so finally, think of z so z is a vector, right? And it's a, say, for example, 5 length vector or a 10 length vector. So if it's a 10 length vector, you can think of, it's called the dimensionality of that vector of 10, right? You can think of it as being a point in a space of 10 dimensions. Okay, and I realize this will be really hard to visualize. It might be hard to internalize as well. So all I want you to think is there is a space. There's a space we can map the sort of space. We can map all the possible values of the latent vector into a space, and that space is called a latent space. Okay, so let's try to understand what this latent space is and why am I talking so much about this complicated stuff. It's because it's really interesting what happens with latent spaces. So usually the length of z or the dimensionality of the latent vector is between like 100 and 512. So that's a space of 100 dimensions or 512 dimensions, right? But for now, let's consider a vector, a random noise of only two values, which is 0.2 and 0.4. Okay, so when you take those two values, the latent space, because it's just two values, right? It would resemble a 2D plane because the dimensionality is of 2. And so you can represent z over here on this point over here. You can see z is represented at 0.2 comma 0.4. And that is the latent space for this particular vector. this particular latent vector. So again, what we're doing is we are mapping all the possible values of Z in a big space. Okay. So something really cool happens when we are training our generator. Okay. As we train our generator, happens is the generator starts mapping dimensions or regions of the latent space into features of the data distribution. So, for example, what that means is, say, for example, I'm making a generator that generates pictures of cats, right? Well, then as we are training our generator, right, it's taking these random values and it's able to sort of say in this big space, if you pick a dimension or a region, it's able to say, okay, that's going to correspond to, like, I don't know, the face of the cat or the nose of the cat or the whiskers of the cat, so on and so forth. So with this sort of latent space, again, I am oversimplifying a bit. I will get back to this. This is not entirely accurate. But with this sort of latent space and the Z value that you start with, you're able to essentially define regions or dimensions or particular specific movements that's able to sort of define features in the end product. So how cool is that? Um, so if you, and if you think about it a bit more, um, so Z is a point in that latent space, right? And if you sort of figured out, okay, this particular, if I moved along the x-axis or if I moved along the y-axis, um, the model sort of maps that to the cat's nose becoming big or small. So if we sort of figure that out and we take Z and move it along the z-axis, along the y-axis, very smoothly, what happens is we get a bunch of very similar images because again we are taking it and moving it very smoothly across each other, and we're getting a bunch of very smooth, very similar images where the nose of the cat particularly is getting bigger and bigger and bigger if we move it along the y direction. So you can pick Z and you can move it smoothly, and that will sort of interpolate it between different features and different regions with the latent space. So this becomes a very powerful concept, especially in something like style GANs. If you've heard of that, that is very, we'll take a quick look at that towards the end. But if you've heard of style GANs or something like that, you can use this is essentially what they use. They don't use this exactly, but they map the latent space into something else, and they manage to use it to mess around with the style. And the final coolest, the thing that I find the coolest is, say, for example, you generated an image of a dog, okay, and then you generated an image of a cat, and you have the latent vectors for both of those. Then you can sort of take an average of both of those latent vectors and interpolate between the features of the two images. So if you take Z vector 1 and Z vector 2 and interpolate them together, you will get a final value, a final generated image that would be between a cat and a dog. So you can use these Z values to interpolate between two images and two data. How cool is that? So I understand completely that this might be a bit hard to visualize and internalize, especially like at the first time that if you're hearing this for the first time. So if this didn't make sense, feel free to ask questions, or if after the stream, I would be available in Discord, MLHS Discord. So you can message me there at 44 not found, and I'll be more than happy to continue this discussion there. So now we are almost at the end of our stream. We're going to address a few problems. Like, great, generators work awesome, GANs work awesome. Why don't we use them everywhere? There are a few problems that happen. First is that if the discriminator becomes very good very quickly, the generator can't really catch up. You can, and I'll talk a bit about this in the next slide. But essentially, if the generator is really good, if the discriminator is really good, the generator just doesn't know in which direction to improve to get better. The second is called mode collapse, in which safe example, if you have a generator, right, and it's learning to make dogs, right? But instead of making dogs, what the generator found was if it made small brown dogs, it's easily able to fool the discriminator. So the discriminator doesn't really understand what small brown dogs are. And then after the whole training process, you'll find that instead of like generating dogs, all it does is generate small brown dogs. It doesn't generate, it doesn't learn the whole data distribution. And that's sort of the whole mode collapses. And finally, the training process is really unstable with GANs. The implementation, doesn't behave how you would think it would work. Um, and okay, I want to quickly pause here to talk about what Muncheng says. When to multiply the two latent spaces, do you get a new image? When to multiply the two latent spaces vectors, do you get a new image? Sort of. So if you like take two vectors and you get an average of them and together, right? You get a new vector, right? You're not getting a new image. If you average them together, you get a new vector. Okay? And you can take that average of vector and you can feed that into a GAN. So you can feed that as random noise. Instead of the random noise, you can feed in that particular latent vector into a GAN. And then the GAN will be able to generate an image that would be sort of a interpolation between the two things, between the features of the two images or two data points. Does that make sense? Okay, awesome. Permatus asks, what do you mean by small dots? I am not sure about what small dots are you referring to. Like about this? Are you talking about latent vectors? Okay, while Permatus answers that, I'll quickly go over the last couple of slides. This very quick thing. So the training process again is very unstable because there are two models and both of them have to be trained. So by definition, it's an additional layer of complexity, and that just becomes very weird. Then there were some oversimplifications that I made. So the first thing was the loss function that I showed you. That is what was. So we don't practically use that loss function anymore. So what happens is when the discriminator becomes very, very good, faster than the generator does, the discriminator essentially points at the generator and says, okay, all of this is wrong. None of this is right. And the generator just doesn't know where to go after that. So the gradients vanish. It doesn't know what next step to take. And so that sort of a loss function doesn't work very well with the generator. It's called the saturating loss function. And so what we do is instead we use a slight variation of the loss function within our GANs today. Secondly, the latent space isn't interpretable by humans. These are like, so I talked about how a particular dimension is like, we would refer to cat's nose getting bigger or smaller. That isn't really how it works. They are internal encodings generally that only the model understands. And there's like no guarantee. Of course, randomly it might happen that a particular dimension might refer to like a cat's nose, but there's no guarantee that a direction or a region or anything like that in a latent space would definitely like correspond to a meaningful concept at all. The third thing is that lower loss doesn't always mean a better quality of data samples. Throughout the training process, the loss oscillates widely. Oftentimes, the loss is reduced, the error rate is reduced, but our visual quality doesn't get any better. Oftentimes, the loss rate is increased, but our visual quality still gets better because the generator is exploring like a new part of the data of the data distribution. So loss isn't the perfect metric that I made it out to be. So that's what I wanted to clarify. These were some oversimplifications that I went through. Then some examples. So there's DC GAN. So DC GANs is essentially the one that standardized using CNN. Think of CNNs as neural networks, which help, which are really good on seeing vision tasks, on convolutional, on image-based tasks. So CNNs are really good at that. There's Pix to Pix, which did like image to image translation. It needed labeled pair data, but like if you gave it a sketch of a shoe, it was able to generate a complete picture of shoe. Then there's like CycleGAN, which is very similar to Pix2Pix, but it can learn from unlabeled data. So it's very cool in that way. And then there's this StyleGAN. StyleGAN is probably one of the most popular and famous ever GAN implementation. And what this does is it uses a mapping network to essentially, we talked about the latent space, right? So it essentially maps the latent space into a styled space. And this, we won't go into details of how this works. If this seems interesting, and it is, please look into it online. It's very interesting. I would definitely recommend that. What this does is essentially it allows you to go through like essentially it allows you to use vectors and sort of merge styles together. If you've seen in original, like before diffusion models took over, if you've seen like AI filters and that sort of stuff, that was probably some implementation of StyleGAN. StyleGAN was very popular. There was also this very famous website called thispersondoesnotexist.com. I'll quickly post that in the chat. Do that. Give me just a sec. Oh, thank you. Quinn's there for me. So Quinn quickly posted that. And this person does not. This is very cool website. If you go on there, it uses a StyleGAN tool to generate a new image, new facial image every single time that you sort of every time that you reload the page, it generates a new image of a person for you every single time. So it's the first time that that image has ever been generated, and likely it's the last time it would be generated. So that's a really cool implementation. And in 20, I think this was released in 2019. This was a huge deal. Still is today. So with that, um, there's also another link I wanted to share. I don't think we have time to go over the visualization for now, but this is another link. And if you want to see how GAN training works in like real time on like a data set, you can definitely take a look at this. It's made by Google. The Google AI team. It's awesome. It shows you exactly how gradients and generator and discriminator work together to thing and how the loss works together. So if you want, please play around with this. This is probably one of the best sites I found for GAN for visualization on GANs. So yes, with that, let's quickly recap the very core concepts of GANs. Um, GANs are made of two submodels: generator, discriminator. The discriminator gets really good at determining our domain and data distribution, which is like feeds us. The generator generates completely random values and shows that to the discriminator, which gives feedback on whether the generated value is a real sample or if it was a fake sample. And then after taking that feedback and adjusting its weight and several iterations, the generator then becomes good enough to fool the discriminator and make like identical data to its domain. So the fake samples are able to fool the discriminator, and it's like good enough then to be able to use in real life applications. And with that, I am open for a few questions. And that's it. That's it. We are at the end of the slides. I am extremely sorry for taking a much longer time than I thought I would take. But yeah, that's technical streams for you. So yeah, Permatus has I see Quinn here. Hello, Quinn.
Hello. Well done. I just want to say that was really awesome. Thank you for doing that. I think we're very tight on time. So unless there are some like immediately kind of jumping out questions, I think we'll wrap it up here. As always, as Yash has pointed out, if you want to chat about this in the MLH Discord, please do so. In any of the channels, I think probably GenAI Week is the one to aim for. I think possibly you've got some hackers asking about reviewing the slides.
Sure. I'll get back to you with that. I think there's a way, if you've registered for the event, if you're registered and checked in, I think I can send you the slides over. So make sure to do that.
Yeah, that's a really good shout out. So I think the check-in link is way up in the chat. I will throw it up on the screen once more. And also as a little reminder, if you've been in a stream before, you probably heard this, but we really like to get feedback. We love to hear what you loved about the streams that you're in and what you think could be improved as well. And yeah, we want to make sure that the streams are really great for you as hackers. So please do give us feedback. I'm going to pop the link for that in the chat now too. Awesome stuff. Okay, I think with that, we'll end it there. Thank you very much, Yash. Thank you very much, hackers, for coming. I hope you've had a really good time. I've certainly learned a lot. And we'll say goodbye now. All right. Bye-bye, everyone.
Bye.